Hello, this is the section 1.7 lesson. Earlier this chapter we introduced the idea of disjoint events. In this section we're going to introduce a somewhat similar related idea that we call independent events. And so let's give a formal definition of the idea of independent events. Two events, A and B, are said to be independent if the probability of A and B equals the probability of A times the probability of B. If they are not independent, they are said to be dependent. Okay? Now, the probability of the intersection is something we talked about with the multiplication rule. Multiplication rule says we take the probability of A times the probability of B given A. But if they're independent, we don't have to calculate that conditional probability. All we need to do is take probability of A times probability of B, and they're all done. Okay? So informally, what this means is that the occurrence of one event does not affect the probability of the other event occurring. And so to illustrate what this means, let's look at this example. So a student has an 8:30 a.m. statistics test and is worried about that her alarm clock will fail and not ring. So she decides to set two different battery-powered alarm clocks. If the probability that each clock will fail is 0.05, find the probability that at least one clock will ring. Okay? And so we're going to set these two alarm clocks, and they're battery powered. And so what happens to one probably isn't going to affect the other one. So let's let F1 and F2 be the events that the first and second clocks fail. And we're going to assume that these two events are independent. In other words, we're going to assume that what happens to clock 1 has no effect on clock 2. That sounds like a reasonable assumption. Okay. And so we want to find the probability that at least one alarm clock rings. Well, at least one means that one rings or two rings. And so if I wanted to calculate this probability directly, I'd have to find those two individual probabilities, add them up. That's more work than I want to do. So let's try using the idea of complements. And so the complement that at least one rings is that they both fail. Well, both fail means that F1 and F2 occur. And so because these are independent, we can simply calculate this probability by multiplying the two individual probabilities. Well, the problem says the probability that each one fails is 0.005. So we plug those numbers in, do the arithmetic, and there's our final answer. So the probability that at least one will ring is almost 1. Not exactly 1, but very, very high. And so that's what independence allows us to do. We calculate this probability of the intersection by simply multiplying the two probabilities, and we're all done. Now next we're going to extend this idea of independence to what we call mutual independence. And this is really just a generalization of independence to more than two events. So there's two parts to this definition. First part, three events A, B, and C are said to be pairwise independent if every pair of events we can calculate the probability of the intersection by simply calculating the product of the probabilities. Okay? Then they're said to be mutually independent or simply independent if they're pairwise independent and the probability of A intersect B intersect C equals P of A times P of B times P of C. So really not a whole lot of new ideas here. We're just extending this idea of independence to three events. Now we could extend this further to 4 events or 5 events or any number of events. But the idea here is the same. They're independent if we can calculate the probability of the intersection by simply multiplying the probabilities. Okay. So let's apply this to one last example here. So suppose that on a college campus of 1,000 students, and we're going to refer to that as the population, 600 support the idea of building a new gym and 400 are opposed. The president of the college randomly selects 5 different students and talk with each one about their opinion. Find the probability that they all oppose the idea. Okay? So we're selecting 5 students from this larger population. We want to find the probability that they all oppose the idea. Okay? So let's define some notation. So let's A1 be the event that the first student opposes the idea, A2 the event that the second opposes it, A3, A4, A5 defined similarly. Okay. Now let's make an observation here. These events are dependent since the selections are made without replacement. Once we select that first student, we're not going to take the chance of selecting that student again, so that affects the probability that the second student supports the idea, which affects the third student, and so on and so forth. So these are dependent. So in order to calculate the probability that they all five oppose the idea, so this would be A1 and A2 up to A5, the probability of A1 is 400 divided by 1,000. Because there's 400 students that oppose the idea, 1,000 total. Now, the probability that the second student opposes the idea, to calculate that, we have to take into account the occurrence of event A1. Once we select the second student, there's only 999 to choose from. 399 of them oppose the idea, so there's the probability of A2 given A1. Probability the third opposes the idea is this. The fourth and the fifth, those are all calculated similarly. Okay. Now we do that arithmetic, and that comes out to be about 0.01. Okay. But now let's do a hypothetical situation. Suppose the selections are made with replacement. So that means the president is going to select a student and then put them back, and there's the possibility that student could be chosen again. Now you may ask, why would he do that? Well, he really wouldn't, but for the sake of argument, let's just suppose he does. Okay, so now when we replace the students, the events are independent. Now what that does for us is it simplifies our calculation. So I want to know the probability that I'll oppose the idea. Probability that the first opposes the idea is 400 over 1,000. Now because we put that student back, the probability the second opposes is 400 over 1,000. So all these numbers are 400 over 1,000. And so that's 0.4 raised to the fifth power. We do that arithmetic, and we get, again, about 0.01. Okay? So working with independent events simplifies our calculations a little bit. Not a great deal, but it is simpler. Okay? So now here's the real point of this example. Let's look at this observation. When we did it without replacement, the probability was 0.010087. When we did it with replacement, treating things as independent, the probability was 0.01024. Okay. Well, those two probabilities are practically the same. Not exactly the same, but for all intents and purposes, they're practically the same number. Okay. So what this illustrates is that in some cases, we can treat our selections as independent even though they technically aren't. Treating things as independent simplifies our calculations, and we get a very good approximation of the actual probability. So this idea is stated in what we call the 5% guideline, which says that if no more than 5% of the population is being selected, then the selections may be treated as independent even though they are technically dependent. Okay? So that's what we have here. We selected only 5 students, and that was much less than 5% of the population. We treated them as being independent. We got this probability when the true probability was this, which is a good approximation. Okay? Now you may ask yourself, where does the number 5% come from? Well, there's nothing magical about that number. It's just a general guideline that's often used. Now this 5% guideline we're going to use in next chapter when we talk about binomial distributions.